Hello, in this video we will talk about vapor pressure. So, what is vapor pressure? Easiest to start with a hypothetical. So initially, you have a sealed system, so there's no exchange of matter with the surroundings. And you have a vacuum above this liquid that's in the sealed system, which means there's no gas molecules above the liquid, which the liquid's down here. Okay, so initially, the gas molecules will have absolutely no resistance to evaporating, and they'll evaporate quite readily. Now, after some time, however, the molecules that have evaporated now start to condense and rejoin the liquid. But then this is balanced out by more molecules evaporating and then molecules condensing, and eventually you reach a point where the number of gas molecules in the space above this liquid is constant. And the rates of evaporation and condensation are the same. So new molecules enter the gas phase at the same rate as molecules leave the gas phase by condensing. And so this is an equilibrium, and we call it a dynamic equilibrium because the process is still happening. It's still evaporating and condensing, but the overall amount of molecules in the gas phase is not changing. And so at equilibrium, the pressure in the space above this liquid is known as the vapor pressure of the liquid. So liquids with a high vapor pressure are volatile, we call them. And what do you define as high vapor pressure? Well, more than water, say. Now, vapor pressure increases with decreasing intermolecular forces. So when there's lower forces holding the molecules together, then they can more readily escape into the gas phase, and this creates a higher pressure above the liquid. The reverse is true. If you have higher intermolecular forces, you have a lower vapor pressure. Vapor pressure also increases with temperature. At a higher temperature, there's more thermal energy in the sample, and this provides the energy needed for molecules to leave the liquid and join the gas phase. And so more of them do so, and the vapor pressure increases. So this chart I took from Wikipedia, and it gives some examples. And the units we're most used to working with are probably millimeters of mercury over here. And okay, let's take a quick look at this. The first one is tungsten, which is a solid. Solids can have a vapor pressure too. Probably the best example is carbon dioxide. It's a solid, but if you enclose the system, that will exert some pressure. And then water's right here. At 20 degrees Celsius, the vapor pressure is 17.5 millimeters of mercury. Now, if you remember last semester doing problems where you collected a gas over water, in the gas stoichiometry section, you had to deal with the vapor pressure of the water. And so here's the vapor pressure of the water again. Now you keep going. Maybe another notable one here is butane. So this is the gas that's in lighters, and it has a vapor pressure that's above atmospheric pressure, which means it's a gas at room temperature. How it sits in your lighter is that it's under some pressure inside your lighter, and that small amount of pressure turns it back into a liquid, which we'll talk more about that when we get to phase diagrams. Okay, so let's take a look at how the vapor pressure changes with temperature. And so the blue line is water, and so as you increase the temperature, the vapor pressure increases, which we talked about. And now you reach a point where the vapor pressure is equal to the atmospheric pressure, which at 1 atmosphere, say the environment you're sitting in now, is 760 torr. And so above this point, the atmospheric pressure really can't do a good job of holding the liquid molecules as a liquid, and then your liquid boils and it turns into a gas. And so that is actually the definition of a boiling point, is when the vapor pressure equals atmospheric pressure. For water, this occurs at 373 Kelvin, which is 100 degrees Celsius. For ethanol, which has lower intermolecular forces and thus a higher vapor pressure overall, it reaches this point sooner, say, at a lower temperature. So the vapor pressure equals the atmospheric pressure at, say, 78 Celsius, so it has a lower boiling point than water. Now, another thing that's interesting is, say you live in Denver and the atmospheric pressure is lower because you're at a higher elevation. And now this point is at a lower temperature. Maybe it's 5 degrees lower. And so your water in Denver will boil at, say, about 95 degrees Celsius. So if you're trying to cook something, everything's boiling at a lower temperature. And so this is why, say, on boxes of cake mix, there's sometimes high altitude directions. Because everything's happening at a lower temperature, you need to change the recipe somewhat. Okay, so that's vapor pressure. And then another way to express vapor pressure is with relative humidity. And we typically only do this for water because that's the gas that is in the environment that we're breathing and living in. And so relative humidity is just the current vapor pressure of water in the air divided by the equilibrium vapor pressure of water. So this equilibrium vapor pressure is the highest vapor pressure you're going to get at this temperature. And then you multiply that by 100. And so relative humidity is just a useful measure of how humid the environment is. So if relative humidity is really low, then maybe that's desert dry. If the relative humidity is really high, then that's the South in the summer. And so I know some people with sensitive scientific instrumentation, they keep a relative humidity meter on the wall in their lab. And if the relative humidity gets too high, it might hurt their equipment. And then they go have a heart-to-heart with the HVAC installer. So that's vapor pressure and relative humidity. That's all we have for this video, so thank you for watching, and so long for now.